like electrostatics or magnetostatics, which is something you study in Physics 232. Anyway, these are Maxwell's equations. So it's fun to look at the third identity and see what this says about the electric and magnetic fields. All right? So that's one of the reasons, of course, we study differential vector calculus, is to better understand the dynamics of electromagnetic fields, their interaction, their interrelation, their time evolution, their propagation, how they give, how they arise and respond to the presence of charge and current. Okay, anyway, so let's look at this identity for the electric field. So we have the curl of the electric field is equal to the gradient of the divergence of the electric field minus the Laplacian of the electric field. So by the way, this is a vector, right? I mean, when this acts on a vector field, it gives you a vector of Laplacians. Like it's this del squared f would actually be del squared f1, del squared f2, del squared f3. That was, I think, your question that I didn't quite answer. Sorry about that. Yeah. Yeah. You were justifiably confused. Sorry. I got distracted from the true nature of your question. So look at that. Now, I should give you some names. This is Gauss's equation. This is Gauss' law. This is this is Faraday's law. This is the no magnetic monopoles equation. No magnetic monopoles. Kind of a long name. There it is, though. And then this one down here is Amperes Law. Now, I should emphasize these are special cases of Gauss's law, Faraday's law, and Amperes Law. The special case in the sense that we're outside, we're in the vacuum. There's no charge and current. Okay, it's just the electromagnetic fields governed by Maxwell's equations. Let's see what happens. So what we have is what? What's the curl of E? Was what? Yes, the curl of minus partial B partial T, right? What's the divergence? So the gradient of 0, well, that's easier, and minus del squared E, all right? Now, the time derivative and the nabla commute because they're independent. Space and time are independent. So I have minus partial T of the curl of B. What's the curl of B? Amperes law, right? So this is minus partial T of mu naught epsilon naught partial E partial T is equal to minus nabla squared E. I can clean this up. What this is mu naught epsilon naught partial squared E partial T squared is equal to nabla squared E. You guys are taking, some of you are taking Physics 231 right now. Have you studied waves yet? Unfortunate. In the study of waves, you'll learn that 1 over v squared partial squared y partial t squared is equal to partial squared y partial x squared is what's known as a wave equation. The coefficient here is the speed squared. So what we just derived is Maxwell's equations imply a wave equation for the electric field. What's the speed of this wave? One over v squared is equal to mu naught epsilon naught, right? So therefore v is equal to 1 over the square root of mu naught epsilon naught. Yes?
Does this mean in vacuum or in vacuum?
Yes. I mean, it means the same thing. So there you go. I mean, whatever. But yes, in the absence of matter and out there, you know. Like that really, really boring movie with, what's her face there?
Gravity.
Yeah, that one. Yeah, you knew what I was talking about. Don't ever see that movie. My gosh, what an awful movie. Sorry. Oh, it was an awful, awful movie. If you haven't seen Interstellar, on the other hand, man, wow. Incredible. Anyway, so what is this? Well, I haven't told you yet, but mu naught and epsilon naught are experimentally determined constants. This mu naught is the permeability of free space. Epsilon naught is the permittivity of free space. In fact, this works out to 3 times 10 to the 8th meters per second. So what this little calculation shows you is that the electric field satisfies a wave equation, and the speed of that wave just happens to be the speed of light. And the same, almost the same calculation will show you that mu naught epsilon naught partial squared b partial t squared is equal to nabla squared b, all right? That's also, very similar calculation shows you that. So the electric and magnetic fields satisfy wave equations, and the speed of the wave is the speed of light. The interesting thing about this calculation is it's done for essentially an arbitrary coordinate system. But the speed depends on the permittivity and permeability of space and time itself. Maxwell's equation suggests that the speed of light is independent of the frame of reference in which you're looking. It's built into Maxwell's equations, the idea of special relativity, the idea that the speed of light is the same in all frames of reference. We didn't have to take electromagnetism and modify it to make it fit with special relativity. It came to us already with special relativity built into it. Once 19th century physicists came to terms with Maxwell's equations and, on the other hand, Newton's equations, classical mechanics, they had a choice to make. You can't have both. They're mathematically inconsistent for this reason. The coordinate change which are allowed by classical mechanics are what are called Galilean relativity. In Galilean relativity, velocities add. If I'm on a train and I throw a baseball in the direction of the train, it's going faster. Why should that be any different for light? This says that light behaves differently in terms of addition of velocities. It says the velocity of light is independent. It's just a property of space and time itself. That's weird from the viewpoint of classical mechanics, where you might suppose that if you shined a flashlight on a train, it would go faster than if you just shined it by the side of the road. But no, speed is always a property of space and time itself. Or the vacuum, the luminiferous ether, as they would think of it. Now, they chalk this up to being there's some kind of, like I said, luminiferous ether. But that came with other problems, which the Michelson-Morley thing eventually showed was problematic. But honestly speaking, folks, when Einstein came up with special relativity, he did it because of the mathematical structure of electromagnetism, not because of some experiment. So let me show you the derivation of this, and then we'll call it a day. Otherwise, my battery is about to die. We may not even make it to we may not even make it to the. Oh man, come on! So I've been explaining to you the story on page 343 of my notes. Come on. Come on, you can do it. You can do it. You can do it. You can do it. Here we go. So, the curl of the curl is this, which is that, which is that, which is that, which is that, which is that. which is that, which is that, which is that. There you go.
Okay.
See you tomorrow.